This is lab 5 for Faraday's magnetic braking. This is the contents, the introduction, purpose, assumptions, fundamental setup, observations, and computation model code, and then questions asked and the answers at the end. Then this is the introduction and the purpose. The purpose is to observe the magnet falling through a conductive tube of aluminum and apply Faraday's law to it and to see how, what changed and how it's happening. And then to compare what happened in the real life experiment to the glowscript simulation. And so the results were 1.314 seconds in the real life experiment and 0.605 seconds in simulation. Simulation was inaccurate to my real life observations. These are the fundamentals of Faraday's law, which is EMF equals change in magnetic flux, or negative change in magnetic flux. And then Newton's second law, which is F equals ma, or mg. G is the acceleration of gravity. Newton's third law, which is an equal and opposite force. Ohm's law, which is I equals VR, EMF over R, and magnetic force in a loop. So 2 pi r times the magnetic field sine theta being cross product of the magnetic moment of magnet and magnetic field, and then the absolute value of the magnetic flux over time, which is this formula right here. It's a lot to read, but this is implemented in glowscript. And then this is Biot-Savart law, which was used for mu and magnetic field. So this is the experimental setup. The bar magnet with a mu from lab 3 in the conductive aluminum tube. The magnet was dropped to the tube. So this is how the lab went through and was observed to be falling slower than usual through it. The North Pole is found in the magnetometer app, and I recorded it falling 5 times in the data table on the next slide. So these are the values of the magnets of the tubes. These are the tubes' width, length, and radius. And then these are some assumptions and idealizations of this lab. Air resistance acting on the magnet is negligible, and the gravity and magnetic forces from the aluminum tube and magnet are the only forces acting as it falls. So for this diagram, there's an air vector going down for gravitational force, and there's an induced current going either in clockwise or counterclockwise direction. And this induced current makes a magnetic force that goes upwards, canceling some of the gravitational force that's coming down, making the magnet fall slower. These are the 5 trials of the muse from lab 3, which is 5.519 amps times per meter. And then the trials are 5 trials, and the average out to 1.314 seconds. So this is the glow-shaped model with the magnet falling through it. So this is like almost at the top in the first half, and this is halfway through, and this is at the bottom. All of this took 0.0605 seconds and for the calculation to happen in glowscript. So this isn't the actual time because I changed the rate, but it took about 0.61 seconds for it to fall through, which is very different from the time I got in the actual lab, which was 1.314 seconds. So here's my code. This is all the values of the tube and they're the values of the magnet. This is visualizing the magnet, so the blue and red. This is calculations for the magnetic field. And then this is the flux, the magnetic force, I mean. This is getting all the data for the magnetic force and the gravitational force canceling out. And it was all plotted on the tube to make it fall through it with the times. And at the end, the time was given in the box. So to analyze why my times were so different compared to the real life lab, I think because there's probably inaccurate measurements of like the mass of the magnet, or the code was a little different compared to what it should be, so the numbers were off. I can say these are probably the sources of error because during the lab there was no like blemishes or anything on the magnets, or the aluminum tube was fine. There was nothing missing from it. So that's why I think the time is a little different. These are discussion questions. So what if holes or slots were cut into the tube? The induced current would be interrupted that goes around the aluminum foil, and the magnetic force would be lower. The lower magnetic force would lead to a smaller time, and the magnet would not be as affected as much. What if the resistivity of the conductor were reduced to as close as possible to 0? the dynamics of the magnet would change because if the reducer resistance was really low, close to zero, when you divide the voltage or the EMF by it, the current would be very large. And since the current is much higher, the magnetic force generated by the aluminum foil going upwards on the magnet that is going downwards would be much higher, so the magnet would fall even slower and there would be a much higher time